So now let's talk about coordinate bond. So here we have coordinate bond. Now coordinate bond, we have previously seen the covalent bond, and coordinate bond is formed by Lewis base interaction. It is the interaction between a Lewis base and acids. Now it is also known as dative sigma bond and intramolecular bond. So how it is dative sigma bond? It is a donating bond, okay, from A to B. So it is a sigma dative bond. It is donated by A and accepted by B. So here when a covalent bond is formed in which bonding electrons are unequally shared between bonding atoms, and then it is named as a coordinate bond. So when covalent bond is formed when bonding atom are unequally shared, okay, how they are unequally shared? Now we have A should have a lone pair, the condition, okay, it is always considered a sigma bond and represented by arrow sign pointing toward acceptor ion. So we will be having our donor atom and we will be having an acceptor atom. So donor atom should have a lone pair and acceptor atom should have a vacant orbital. The donor atom is generally categorized as a Lewis acid and acceptor atom is generally categorized as a Lewis base. It should have vacant orbital. It could be vacant p orbital, it could be vacant d orbital. So while considering its hybridization, we can see that the bond, we can see that it should have a lone pair or not. We will see later hybridization. First of all, in that covalent bond forming, we will know whether it could have a bond or not. So air forming B. So like A should have a lone pair condition and B should have a vacant orbital. So now formation of addition product. Now these are the examples of that coordinate bond. So coordinate bond, it should have a lone pair and should have again vacant orbital. So we know boron in the total number of electrons are boron in 5. Okay, so when this is the electronic configuration, when boron get excited state, it gets into excited state. In excited state, it has 1p orbital empty. Okay, when it gets excited state, this electron jumps here, and here we can say it has 1 empty p orbital. So that's boron has a 1 empty p orbital. Okay, so now this lone pair. Now if we see the nitrogen has again lone pair. 1 lone pair nitrogen have. So that lone pair it donates directly to the boron. So coordinate, here it is a coordinate bond. Okay, so this bond, okay, the donation is a coordinate bond, and that remaining are covalent journal bond. Okay, these are electron shared atom, and these are formed by sharing of electron, and these are formed by unequal sharing of electron. What do we mean by unequal sharing? We have already seen the unequal sharing means the shared electron are very less. Just means one nitrogen has. These bonds were formed by sharing of equally sharing. Okay, these are formed by equally sharing. Okay, these bonds were formed by sharing. Okay, equally sharing. Now we know this bond is formed by unequal sharing. Now further, if you see, in form of hydronium ion H3O plus. So H3O plus, we know water has a 2 lone pair. If we see the structure of water, now hydrogen has empty orbital. We know hydrogen is purely empty. Okay, so we know that H2O, this is the H2O. So oxygen donates lone pair here. Okay, oxygen donates lone pair. So this bond is known as again coordinate bond. Okay, this bond is known as again coordinate bond, and that when coordinate bond is replaced by covalent bond. Okay, here it is replaced by covalent bond. When it is replaced by a covalent bond, then donor atom will have positive sign and acceptor will have a negative sign. So we have seen already this was H plus. Okay, now when this was H plus, now when we going to shift bond this to covalent bond, then we will give plus here, negative here. Now plus and negative, it will make 0. Now oxygen will have a plus sign. So that's how we will see whether it is a positive or negative. Okay, so now if you see formation of ammonia ion, again nitrogen has a lone pair. When it donates its electron to the lone pair H plus, so we know here there will be a formation of covalent. Again here will be a formation of coordinate bond. Okay, in coordinate bond there will be formation. Now we know that when H is has plus charge, when it will accept an electron, it will have negative charge. Now nitrogen will have plus charge. Okay, when this bond is converting into covalent bond. Okay, coordinate bond is converting into coordinate bond. Here it is getting into covalent bond that we have seen already. That is getting into covalent bond. So that's how we see the structure. So now these are the very important point. Non-metal that will stable with negative charge, and when there will be a non-metal that will be stable with negative charge. If we talk about oxygen, nitrogen, sulfur, chlorine, these are non-metals. Okay, non-metals. So we know these are stable with negative charge. Okay, negative charge means it is stable with O minus is stable as compared to O plus is not stable. Okay, that's how we can see nitrogen N minus is stable but N plus is not stable. So when there will be non-metal, this will be stable with negative charge and unstable with positive charge. Metal with positive charge will be stable and negative charge it will be unstable. So metal, if we talk about magnesium, so we know Mg plus 2 is stable. When we talk about Mg plus 2, it is stable. Now when we talk about Mg minus, we know this is very unstable. Okay, it is very unstable, or we can say it is unstable. So now there we know that H2O, in H2O we know that the oxygen only can donate one lone pair. Okay, can donate only one lone pair. Okay, can donate only one lone pair. Okay, because we know O plus 2 is very less stable. Okay, we know O plus is still less stable, but we know O plus 2 will be quite very unstable, so we cannot form H2O plus. So there is a question, correct formula for hydronium ion. We know that hydronium ion, the general formula is H plus N H2O N. Okay, so this is an example. So we know that H2O N, N could be 1, 2, 3. When we put the value 1, 2, 3, then we get A, B, N. C are the answer. H for O2 is not the answer. Okay, now we talk about behavior of boric acid in water. So this is a boric acid. Okay, we generally how we categorize acid, when we have an areneous acid HA. When that HA acid will convert into H plus and A minus. So we know this type of conversion, we know it as a that acidic character. Okay, we categorize it as a acidic character of the acid. Now if we have like example HCl will give H plus and Cl minus. So this is generally acidic character. Okay, this is the acidic character of HCl. Okay, now we know HCl, it is the acidic character of HCl. So here, and then that's why it is acid, because it is adding here in the water, in the solution over here H2O, and H plus Cl is adding H plus Cl. Okay, so it is adding H plus Cl. So now we have H3BO3. In case of H3BO3, what happening? It is acid. Okay, it is known as boric acid, but it is not donating its OH. So it is not donating. It's not donating its H plus. Okay, it is not donating its H plus. So now we know it is not donating H plus. Then still it is an acid. Then still it is an acid. It's an acid. How? We know that the water has a Lewis base here. Okay, it is considered as a Lewis base. Water here we are considering as a Lewis base. Now when we considering it as a Lewis base, it will donate, and here a lone pair Lewis acid. Then H2O. Okay, then it will form H2O. Okay, so boron will having O, H and S. There will be a positive charge. Now hydrogen will leave. So now it is now what is happening here in case of H3BO3, we have a container where we have H2O. So what is happening? Boron is eating, means boron is accepting H plus OH minus. Now there is an increase in the concentration of H plus. Now indirectly it is increasing the concentration of H plus by consuming the OH part of water. So it is an acid. So boric acid is only oxygen acid, will never release its own OH plus in water, because when it dissolves in water, it being electron deficient species accept electron pair from OH minus ion of water molecule and releases H plus in water. That's why it acts as a mono basic Lewis acid. It never acts as a areneous acid under H2O.